Hello grade 11s. The next homologous series that we're going to have a look at is called the carboxylic acids, and these are organic acids. Every homologous series has a functional group that helps us identify which homologous series the organic compound belongs to. And so we are looking in a carboxylic acid for a carboxyl group. Now, a carboxyl group is when there's a carbon with a double bond to an oxygen. That is actually called a carbonyl group. And we've also got the single bond to the OH group, which is a hydroxide. So it's not just a hydrogen that's replaced with a hydroxide, otherwise that would be an alcohol. What we have is this hydroxide, which is an OH, bonded to a carbon that is bonded to a double bond to the oxygen, so bonded to a carbonyl group. And together, those two, the carbonyl group and the hydroxide, are called a carboxyl group. And so if we see the carboxyl group and it's on the end of the molecule, so it can either be on the first carbon or the last carbon, as long as it's on the end of a molecule. So we're looking for a carboxyl group, and that is the functional group that identifies it as a carboxylic acid. Now, we always make the carbon, which is attached to the double bond to oxygen, and the OH group, we make that one carbon 1. So in this case, we don't have any branches. So we've got 1, 2, 3 carbons. And so if we didn't have this functional group, this would just be propane. But what we do is when we've got a carboxylic acid, because here we can see on the very last carbon, which we would make carbon 1, we have the carboxyl group, and we replace the E in propane with oic acid. And so the name of this carboxylic acid is propan because of the 3 carbons, and it ends in oic acid. Now, if you remember, for the homologous series alkanes and alkynes, the functional group is the double carbon-to-carbon bond or the triple carbon-to-carbon bond, and that takes preference when numbering the carbons. When we have haloalkanes, what we have to do is, if there is no branch, then we number the side, we give carbon 1 the side closest to the halogen, but if there are branches, we number just closest to the substituent, whether it's an alkyl substituent like a methyl or whether it's the halogen. So the halogen doesn't take preference. Then we went on to alcohols, and in alcohols, the OH group takes preference. So we start numbering the carbon closest to the first OH group. Now it works the same when we have branches and the carboxyl group. So as I told you, the carboxyl group will take preference and we will make that carbon 1. So in this organic compound over here, we need to identify the longest continuous chain that contains the carboxyl group. So there is our longest chain, which has 4 carbons. So we know that this is going to be butanoic acid. Now, over here, we have an alkyl substituent called methyl, and over there, we also have an alkyl substituent called methyl. So we have 2 of them, so it's dimethyl. Now, whenever we have 2 of the same and we use the word di, we have to give 2 addresses. Now both of these are on the same carbon. It's on carbon number 3. So this would be 3,3. We have to give both of the addresses. 3,3 dimethyl butanoic acid. So there we have it. 3,3, 2 addresses because it's a dimethyl. The butan comes from the 4 carbons and it ends in oic acid. Now, we can get carboxylic acids that have carboxyl groups on either side of the molecule, and that would be a dioic acid. And if we are naming a dioic acid, because we're using the word di, we have to give an address. So I'll show you in the next couple of slides. I do have an example. So here we have an organic molecule and we have to identify what is the functional group. So here we have the functional group. It's not just an OH, it's also the double bond to O. So that's a carbonyl group, that's a hydroxyl group, and it's on the end of the molecule. So we know that this is a carboxyl group, which is a carboxylic acid. Then we have to identify the longest continuous chain, which is the parent chain. So it has 1, 2, 3, 4. Now remember what we have to do. We have to number the carbon with the carboxyl group, carbon 1. And so this over here would be a methyl group, and it would be on the second carbon. So we would call it 2-methyl. And then we don't leave a space between letters, remember. Then we have 4 carbons, so it's butane. And then because of the carboxyl group, oic acid. So this is called 2-methyl butanoic acid. With this organic molecule, here I have the structural formula. And when you can see all the bonding, it's much easier to name the molecule. But remember, it could also be given in a condensed structural formula. And this is what the condensed structural formula would look like. Remember, we don't show the bonding in a condensed structural formula, and we put the substituents in brackets. So this carbon has 3 hydrogens, so it's summarized there. This carbon has 2 hydrogens. The next carbon has 1 hydrogen, and because it has the CH3 group, we put the CH3 in brackets. Then we've got CH2, then another CH2, and then the carboxyl group we'll summarize as a COOH. Now, before you listen to me explain how to name this molecule, I'd like you to pause the video using the IUPAC rules that I've explained previously, and I'd like you to try and name it yourself first. So, first of all, we're going to make carbon 1 the carboxyl group. So, the parent chain, let me just get my highlighter. The parent chain will be the longest continuous chain containing the carboxyl group. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So that is going to be the parent chain. So if it didn't have the carboxyl group, it would be hexane. And because we've got the carboxyl group, it's hexanoic acid. But we also have an alkyl group over here, an alkyl substituent. So that is a methyl. Now, the methyl is on 1, 2, 3, 4, the 4th carbon. So you can see here the branch doesn't take preference, the functional group takes preference and is named carbon 1. So this methyl branch is on carbon 4. So it's going to be 4-methyl hexanoic acid. So 4-methyl hexane representing the 6 carbons in the parent chain, and oic acid representing the carboxyl group. Remember, the carboxyl group has to be on the end of the molecule. It can be on the first carbon, this side on the left-hand side, and we would name that carbon 1, or on the other end of the molecule. We're still going to have a look in the next slide at a dioic acid. Now remember what I told you. If there are 2 carboxyl groups, then you do have to give the address of the carboxyl group. Let's have a look at that one. Now, if we have a look at this organic molecule, we can see that there's a carboxyl group on the left-hand side and a carboxyl group on the right-hand side of this molecule. And we can see that over here we have an alkyl substituent. So please pause the slideshow and use the IUPAC rules and see first if you can get the name on your own. So remember, we need to choose the longest continuous parent chain that contains the carboxyl group. So we'll have to go from there to there. So we have 1, 2, 3, 4, 5, 6 carbons in our parent chain. So if we didn't have these carboxyl group, it would be hexane. And so we know that it's going to be a hexanoic acid. But now we've got 2 carboxyl groups. So we need to number it. So which one are we going to make carbon 1? Now, what we're going to do is, because we have this alkyl substituent, because we have this methyl, we're going to try and number to get the methyl on the lowest one. So if we made the right-hand side carbon 1 and the left-hand side carbon 6, then you'd see that the methyl is on 1, 2, 3, 4. If we did it the other way around, we made the left-hand side carbon 1 and the right-hand side carbon 6. Then we would have the methyl group on the lowest address. And so that's the one we would go for. So on carbon 3, we have a methyl. Then it's hexane 1,6 dioic acid. We have to say di because now we have 2 carboxyl groups. And we have to then give the addresses of the carboxyl group. If there's just one carboxyl group, we don't have to give its address. We just assume that is carbon 1. But if there are 2, then you need to give the address. So it's 3-methyl hexane, parent chain has 6, 1,6 dioic acid. Did you get it right? Now, carboxylic acids are found all over nature. And we can also, there's a lot of uses for carboxylic acids. So ethanoic acid, which the common name is acetic acid, is most commonly used to make vinegar. It's used as a flavoring, as preservatives. It's used with other chemicals to make drugs. For example, makes aspirin, dyes, paints, insecticides, and plastics. Then methanoic acid, and its common name is formic acid. That is actually when a red ant bites you. The reason it stings is because there's methanoic acid in that bite. And so what they use that, so in nature, it's in red ants. And to get methanoic acid, they actually used to distill red ants to get the methanoic acid. But it's used in the production of latex, like in the gloves that we use. Then long-chain carboxylic acids are used in making soaps, and benzoic acid, that is a preservative in foods. So there's a lot of uses of carboxylic acids. As I said, they are a type of organic acid, and they're not as strong as, say, sulfuric acid. They're weaker acids than sulfuric acid and hydrochloric acid, and it has many uses.